I'd like to introduce all of you to Dr. Jeffrey Abell. He is Carroll High School class of 1980, and he is a mechanical and manufacturing engineer, the Director of Research and Development at General Motors.
Really nice seeing everybody today. I think you guys are sort of living the same experience I am right now. This is basically what I do all day is, I'm on different kinds of teleconferences. Very rarely do I get to join in a video conference. We just have too many people, in the system, and we're concerned about bandwidth and things like that. So it's really nice actually seeing human beings that I'm speaking with. If we get a chance, maybe we'll go around and see what everybody's kind of interested in. I do have a few slides I like to go through. This is me today. This is me on the day we graduated, and Diane's on, so she was out there somewhere also. You notice I got a lot more hair and bigger glasses and stuff, so that stuff was kind of in style at the time. This is where I work today. This is sort of a famous aerial shot of the GM Tech Center in Warren, Michigan. I work in this big, long building. Not right now, but I work in this big, long building. This is sort of the administration building for research, and we have an entire research complex behind. So today I want to talk a little bit about engineering. As Julie mentioned, I am a mechanical engineer. And so if we want to talk about engineering in general, that's okay. Mechanical engineers specifically really, they look at various kinds of problems and they apply physics, mathematics, different, maybe chemical concepts to solve problems by design, through the processes of design, analysis, manufacturing, or even maintenance. So if we take a look at some of the systems that an engineer would work on, where the term engineer originally came from was in war engines. And so I just put a little picture of a trebuchet over here. If we think about the people that actually designed and constructed the pyramids, they certainly used engineering principles. All the way into the modern industrial revolution, train engines, internal combustion engines, safety systems like this helmet, robotics, various kinds of robotic systems, both autonomous and mobile robots, to industrial robots that we use in automotive plants, manufacturing processes, other kinds of devices like the water screw. This is something that Leonardo da Vinci designed. And all the way from these sort of macro systems, what I'll call macro systems, all the way to systems that operate on a nanoscale. This is a small gearbox that's actually operating at the molecular size scale. So many different kinds of systems. This is, really just scratching the surface. So an engineer, really the process of engineering has to do with taking requirements, conducting some analysis, and then refining that original design and into something that you can actually manufacture and test. And so if we take this example of the trebuchet, we might on a piece of paper or on a CAD system, I'm sure you guys are familiar with CAD systems, we might actually design the trebuchet, concept it, based on some requirements. And so this particular requirement that I put up here, throw a 20 kilogram projectile 300 meters. So really, it doesn't say anything about how we're going to do that. It just says what we want the system to do. So you might think of a cannon, you might think of a trebuchet, you might think of a big slingshot. I mean, there's lots of different conceptual ideas for making this really happen. And then if we actually decide on the trebuchet concept, then we might actually take our original design and analyze it. And, for, a given projectile weight and a given distance, we know what force we're going to have to impart on that and what speed that projectile is going to have to take on at launch. And so we might say, oh, when we actually analyze this, the way that we've designed it, the torque is 2,000 Newton meters, and that might be too small. And so then we need to refine it. Maybe we need to add weight to the counterbalance. Maybe we need to increase the length of the arm, the height of the trebuchet, or the height of the pivot point, et cetera. And then once we refine it and we think we've got a design that's actually going to work, then we're going to build and test it, right? And so, we might get test results that look like this, 275 meters, 310, 290. And so we're sort of in the ballpark, but we're not consistently over 300 meters. And so at that point, we may say, okay, we need to refine this. We might use some engineering judgment and say, we're not consistently in the right range of performance. And so we need to change the design. We may need to, do some of the things that we did before, but maybe do them in a slightly different way. Or we may decide to throw out this trebuchet concept and go with a slingshot or a cannon or something like that. So sort of in a nutshell, in 90 seconds, I sort of described what the engineering process is. And you'll notice that this is sort of in a circle, right? It's in some ways it's serial, but in other ways, this is sort of a never-ending process, especially if we want to refine this design and continuously improve it. And, maybe we make trebuchet version 1, and then a year later, after we have a lot more data, we make trebuchet number 2, et cetera, right? So different versions. One of the things that I want to point out is, I've sort of talked very quickly about mechanical engineering, but mechanical engineers wear a lot of different hats and do a lot of different things. And these are some of the titles that you might see, position titles that you may see, where a mechanical engineer would actually do a great job. So you might see automotive engineer or design release engineer, manufacturing engineer, like what I do. Even some naval architecture or ship design, safety engineer, test and validation engineer, like we mentioned over here. But there's also some other titles that you might be surprised about. So biomechanical engineering. In a lot of ways, biomechanical engineering, although you can specialize and study this in college, a lot of it is, mechanics, the mechanics of the human body, and how do you either improve upon those mechanics or prevent injury, et cetera. Medical doctor. I know several engineers that have gone into medicine, and it provides a great background foundation for a medical career. Intellectual property attorney. A lot of engineers go into law, especially in intellectual property, helping people prosecute patents, and also, developing intellectual property strategies, et cetera. So lots of things, lots of different kinds of careers that engineers can have, with a solid beginning or a solid foundation with engineering. So Julie asked me to sort of give a history, sort of my history, since leaving Carroll to today. I hate to say it, but it's, there's 40 years between when I graduated and, to today. But, we can quickly go through some of these things. And I sort of provided a technology timeline across the top. I know you guys don't remember the days when, there was no internet or email, but I do. And so, the change from the 1960s, I'm sure you guys have heard of Apollo, to today, where we're staring quantum computing, Mars flights, manned Mars flights, autonomous driving, and all the great things that we're talking about today. All of these things sort of built on, our technological framework that we're we're using to sort of create the world of tomorrow. So in 1980, I graduated from Carroll, and then I went to GMI, General Motors Institute. I really wanted to be an engineer. I can hardly remember a time that I didn't want to be an engineer. And I had a great background, not only more or less on the product side, but also in manufacturing. I had an opportunity in 1980 and 85 to actually work in Portugal before I graduated, and I completed my undergraduate thesis there. That was a great experience, a great cultural experience, as well as a work experience. Then I repatriated, and I worked in Vandalia for a little while. There used to be a GM facility there. I met my future wife at work. She went to Ohio State, so we've got a pretty strong connection to Ohio State. Almost immediately, about 6 months later, I got an offer to teach at GMI, and so I joined the faculty, and I went to graduate school. They sent me to graduate school, and so I got my master's and PhD in systems engineering from Oakland University. It's a regional university, kind of like Wright State. They had a great program, and I truly learned a lot. In '94, I rejoined GM in an advanced development group focused on digital manufacturing. And remember, this was in the '90s, and so CAD systems really were not that old at that point, not as mature as they are today. In '94, I went to Daimler Chrysler, a newly formed Daimler Chrysler, as a supervisor in robotics simulation. In 2000, I rejoined GM as a group manager in really more of an engineering business process type group. In 2003, I went to Germany on an assignment in vehicle program support. Repatriated. Most international assignments don't last that long, so I repatriated after 2 or 3 years. I went into CAE, computer-aided engineering, and went into technical management and development in a CAE group. In 2008, I joined R&D, and I started a battery manufacturing research group. This was, if you guys know the Chevy Volt, if you've heard of the Chevy Volt, GM decided that they wanted to build the batteries, not just buy the batteries. And so, when you stand up a manufacturing engineering group and a manufacturing operation, for the first time, generally there's research that has to be done. And so I worked on this for a number of years. And one of our mantras was, we were moving quickly towards the launch of the vehicle, and we were doing research basically at the same time. And we just could not, we had to figure out a way so that everything could work. And so we took on one of the mottos of Apollo: failure is not an option. And so, most of the time when you think about research, some things work, some things don't. In this case, we had to make sure everything worked. So I did this lab group manager role for about 10 years. And in 2018, I was promoted to director and chief scientist. And so now I have about 50 people working for me, working on various types of manufacturing research. And then here I am today talking to you guys. So I just want to leave you with just one more thing. I thought you might be interested, and I'm glad Diane's online, because what are some things that I learned that I still use today? And, I think there's some obvious things, right? You guys are probably on calculus and chemistry and physics and all that kind of stuff. Everybody has to take phys ed. But, an absolutely important aspect of what you're learning is communication, written communication, oral communication. The ability to convey ideas is extremely important, especially in engineering. We deal in really complex topics, and we have to communicate with all different kinds of audiences. And so, this probably some of the most important things that I learned at Carroll were written and oral communication. And so I certainly thank my teachers there. The other thing that you get that a lot of other kids in high school don't get is a connection with your faith. And, beyond the time when you're going to have a career, everybody's going to retire at some point, but you'll always have your faith to sort of fall back on. So, enjoy the time that you have learning about your faith in high school and interacting with people, along those lines. And then obviously, learning about learning and learning to love learning is really important, because especially if you're going to go into engineering, as you saw on my timeline, going from not even having, personal computers to talking about autonomous driving today, you're constantly learning, and you have to learn, you have to keep up with different developments. So that's what I've got. I'll open it up to whatever questions that you guys have right now.
What was one of the hardest things that you had to go through while in school, like during, like even in grad school?
Okay, so the question is, what was one of the hardest things I had to go through?
Yeah, like one of the biggest challenges you had to go through, like say like challenges that you had to face that you couldn't really
Yeah.
head
Yeah.
first.
So, I mean, yeah. So I'll talk about it in sort of two phases, right? So, when I went to engineering school for my undergrad, everybody loved engineering, and everybody was really good at what they did. And so, you guys are probably all really good in math and science. You're going to be among hundreds of people who are really good in math and science. And so, just realizing that, there's a lot of other people out there, and it can potentially be competitive, right? Even getting into engineering school can be very competitive. And so, understanding sort of how to balance, that competitive nature with the fact that you have to, be friends with these people and collaborate with them, right? I mean, there's sort of a human side to engineering as, also there, it's not just, it's not just all the hard technical facts and things like that, right? So coming to that realization, I think was sort of a wake up call. And, you get that really early in, if you go to any sort of technical, technical university. In graduate school, what you realize is you may have a goal, but you may not be prepared to actually achieve that goal. And so, what I talked about lifelong learning, you may have to end up actually teaching yourself some of the things that you're going to need to actually succeed. I mentioned systems engineering, right? That's really a combination of electrical engineering and mechanical engineering. My whole background was mechanical engineering. I didn't have a controls background. I really didn't have an electrical engineering background. I didn't know very much about computer programming. And so I had to learn a lot of that on my own. And, you're going to realize that you can't always, fall back on formal learning. You're going to have to just take your own skills and your own sort of, drive and teach yourself some of these things, right? And learn to ask the right questions.
Why did you choose GMI?
Yeah, so my mom asked me the same question. So I had so I applied to, I think I applied to 3 or 4 different schools, University of Dayton, but I really wanted to go away, right? I know your mothers don't want to hear that, but I really wanted to go away. Rose-Hulman, I don't know if you guys are familiar with Rose-Hulman. And, I went to, they have a summer program, I think they still have it, it's called Operation Catapult, where you spend 3 or 4 weeks at Rose-Hulman and you get to immerse yourself in engineering. My mother really wanted me to go to Rose-Hulman, and then GMI. And I went to GMI because of the co-op experience. So, so co-op was new to me, right? And so, we spent 12 weeks on campus, that was a semester, and then we spent 12 weeks working. And so by the time I graduated, I had about 3 years of work experience. And I just knew, and I don't know how I knew this, but I just knew that in order to really understand what engineers do, I had to do what engineers do. And the way to do that is to really, take advantage of internships, take advantage of co-op experiences and things like that. Obviously you're going to apply what you learn in school to the job, but you can't replace on-the-job experience, especially in engineering. That's really why I went to GMI.
What advice would you give a student trying to get to college?
Certainly you should take those foundational classes, right? And take as many as you possibly can, and can tolerate, I'll say. I'm sure the course description is very different today. You guys probably have AP classes. We really didn't have AP classes. But take as many AP classes as you possibly can that relate to math, including computer programming, or AP Calc, or any of those. Even if you decide to take them again, you'll be surprised the difference between your high school classes, even if they are AP, and college classes. It's just a different level of intensity, I'll say, and a different speed at which they teach. Focus on, you saw my slide that talked about all the different types of things. Don't ignore classes like English and speech, and I don't know what they call them today, but oral communication, extremely important. Anything having to do with creativity is key to engineering. So even like theater arts or music, any of those are, you may be thinking, what is he talking about? But it really does help you sort of unlock the right side of your brain that you're going to need along the way in engineering as well. And, the more creative you are, and the more, I call them dots that you can connect, sort of the technical side with the creative side, extremely important in engineering.
Students were maybe unsure of what field of engineering they wanted to go in. Do you think there's one, like a mechanical, that leads to, preparing them, and they could easily then go more specific?
Yeah, sure. Mechanical engineering is pretty broad. You end up taking core courses that, will include elements of electrical engineering, computer programming, and things like that. And then if you do decide to go into another course, it generally, especially if you change maybe after the second year, it's not that difficult. You can certainly transfer. But mechanical engineering is about the broadest. It's about the oldest and about the broadest. The only, if you're thinking about chemical engineering, that may not translate as well. But certainly, some of the other engineering programs, industrial engineering, electrical engineering, mechanical engineering, civil engineering, a lot of those are really sort of had their roots in, physics and mechanical engineering.
Do you think it's important that they really focus on a particular language? I try and stress that they need to understand programming and, not focus necessarily on the one language. Is there one language that you would advise me or advise them to be somewhat familiar with?
No, not really. I can't tell you how many programming languages I've learned and forgotten in the last 30 years, right? The important thing is that you understand what you can do with a program, with a some sort of model that you're developing. And the basic ideas, right? Looping constructs, functions, the differences between subroutines, scoping, all that kind of stuff. There may be in it, Diane, I don't know if you talk about object-oriented programming at all. We
do.
Okay, good, right. And so, sort of the basics between procedural programming and object-oriented programming, functional programming, things like that. Those are all really important concepts. But as an engineer, you're going to learn, I mean, you're gonna be learning programming and programming languages probably the rest of your life. And, you know, even scripting and prototyping languages like MATLAB. I don't know if you guys use MATLAB at all in school, but those are all really important. But there is no single language. That's maybe the most important thing to learn, because you use the right tool for the right job, and different kinds of programming languages can do different things. And so, you know, start with the basics, get really good at one, and then just realize you're going to have to teach yourself another dozen over the next 15 years or so.
Do you think that there's a certain level of intelligence you have to be at, or do you think some of that success can come from dedication?
Yeah, I mean, I would say no, right? You know, obviously there's, and, you know, intelligence can be measured in a lot of different ways, right? And so, you know, some people are going to be very good at, you know, mathematical concepts. And even though mathematics is a sort of a foundational skill in engineering, it's not the only skill, right? So there are, you know, engineering managers, for example. And, you know, I kind of wish you hadn't asked it that way, because now people are going to say, well, you know, he thinks that managers aren't bright or something, right? But that's not the case. And I would say maybe the better way to think about it is there's different kinds of intelligence, right? There's, you know, maybe technical intelligence, you know, maybe, you know, using mathematics and things like that. But there's also project management intelligence, right? You know, sometimes they call them soft skills. I don't like to call them soft skills, because, you know, you do need to know how to, you know, run a good project and things like that. So I mean, in the end, I would say no, right? You know, if what you're talking about are, you know, maybe what your, you know, grades are in college, even that sort of provides a, you know, a wide variety of responses, right? So, you know, I would say the important thing is that you really decide that engineering is what you want to do, and then go figure out how to do it, right? And, you know, I mean, there's going to be a wide variety of people who are involved in engineering. And, you know, the worst thing that you can do is either think that you can't do it, or think that somebody else isn't good enough to do it, right? Because, you know, one of the things that you're going to learn is I would say the team aspects of solving engineering problems. And you're going to need a wide variety of skills and skill sets and capabilities in order to really solve these problems. So
I think their next class is about to begin. I'm sorry to cut.
Julie, you know, if you want to, I can send you these slides. And if you want to, if anybody wants to ask another question, they can send me an email or whatever.
Thank you so much for joining us today.
Okay. All right. Thanks. See you guys.